and welcome back to Elementary Algebra. I am your instructor, Amy Fuchsteiner, and we are going to be working on Chapter 8 today. Chapter 8 is going to deal with some square roots, so you're going to need a calculator for this. You can use the calculator that's on the computer. You can use the calculator that's on your phone. All of those are fair game. If you have the calculator that's recommended for this class, that's a TI-30. XS2, I think the S stands for solar and a B stands for battery. And there are about 4 different versions of this calculator. So if you have a slightly different version, that's going to make things a little bit difficult. But I will show you where the buttons are on this one. And I will do my best to make sure that I've at least given you hints as to what you should look for should you have a different calculator. All right, let's get started. So we have 4 goals for this section. The first goal is finding the square roots of what are known as perfect squares. So let's talk for a minute about some notation. When we're looking at a square root, let's say we're looking for the square root of 16. All right, a couple of things. This whole piece, all of this, is known as the radical. Okay, that radical symbol is the little one that sort of looks like a mix between a check mark and a division sign. That is the radical. That indicates that we're taking a root of some sort. When the index is missing, the index generally goes up here. That's where the index goes. If it's missing, we assume 2. Or square root. What we have underneath the square root, the 16, is called the radicand. So a little bit of vocabulary. We have the radical, that's what we call the actual symbol. We have an index that's normally up here in a corner, but if we don't have one, we can assume it's a 2. What is underneath the radical symbol is called the radicand. All of this together is known as the radical expression, and that's what Chapter 8 is all about. So, if we look at the square root of 16, what we're asking is what number times itself is 16. So what number, when you multiply it to itself, is 16? This would be 4 times 4 will give you a 16. This is true. 4 is known as the positive square root. Sometimes 4 is called the principal square root. If you're ever asked about the principal square root, we're still talking about 4. All right, so 4 is also known as the principal or positive square root. Now, is there another number that when you multiply it by itself, you still get a 16? And that's going to be a negative 4. Negative 4 multiplied by another negative 4 is still 16. Negative times a negative is positive. 4 times 4 is 16. So negative 4 times negative 4 is the negative square root. All right. So we've done a lot of little vocabulary up in this section. Again, we've talked about what the radical is. We've talked about the index, where it should be. And if you don't have one, to assume we're talking about a 2 or a square root. And we've talked that the number underneath that square root symbol is called the radicand. Now, this radical symbol says what number times itself is 16. Multiplied by itself, or 2 of them multiplied together, is 16, because we're assuming an index of 2 there. If that were a different index, we'd need a different factor. Okay, 4 and negative 4 are the answers to this particular radicand, but 4 or positive 4 is known as the principal square root, and negative 4 is the alternative. All right. You see below in red, I have a huge list of numbers. These numbers are all known as, these numbers are all known as the perfect squares. So at some point in my life, because, I taught mathematics, I teach mathematics, I had to know all of them up to 25. I have them listed here to 24. As we've spoken about previously, I'm pretty sure many of you know this to at least 10, some of you to 12. But if you don't, that's where we want to be using the calculator. Let me place it down here. The squared button on your calculator is generally in the first column, and it's x to the second power. If you see above that, I have a little radical symbol. That's my square root symbol. So if I need a square root, I hit second or the green button to get to the green function. So I'll hit second and then I'll hit x squared, right? We have some practice with this, finding each square root. Now, for each of these, do we find 1 or 2? It sort of depends. Do they ask us for the principal square root, or do they ask us for any square root? I think they ask us for any square root. They don't say just the principal. They just say find each square root. So if we're looking for the square root of 49, do you see how I did that? Let me do that again. Clear, I did second square root, right? Second square root. And now I'm going to type in 49. I'm going to close my parentheses. The square root of 49 is a 7. Your calculator is only going to give you your principal square root. All right? It's not going to give you both options. It's only going to give you the principal square root. So, algebraically, here's the actual rule. If they've only asked you to evaluate it, as in the square root of 49, most of the time, if they do not say, they just want the principal square root or the positive 7. So if we did the square root of of 0.81, so I'm going to do second square root 0.81, right? I'm going to get 0.9. So I don't want that. I want 0.9. And I'm only going to keep the positive or principal square root. If I have a problem like number 3, where I have the square root of 225 over 49, I can break this apart into the square root of 225 over the square root of 49. So the square root of a quotient or of a division problem is the same as the square root of each part. The square root of 225 is 15. The square root of 49 is 7. I know that, but you now know how to do it on your calculator if you did not before. Problem number 4 has the negative square root of 144. Remember, if we're just evaluating, the square root of 144 is 12, and they want the negative of that, so I'm going to put the negative on there. Problem number 5 is the square root of 25 over 49. Square root of 25 is 5. The square root of 49 is 7. So I'm going to leave this at 5/7. Square root of 0, 0. The only number times itself that gives you 0 is 0. So 0 times 0 is 0. Notice that there are no negative numbers here, right? We're going to now do a little work with approximating square roots. So there are 2 different types of square roots. Well, 3, actually. We have the rational square roots. That is if you asked for perfect squares. So the square root of 16, the square root of 25, the square root of 49. All of these that we did are known as rational square roots because they are all perfect squares. Irrational would be the square root of 15, the square root of 20, the square root of 45. All of these are known as irrational. They are irrational because they are not perfect squares. Then we have the the ones we can't do, right? So if you have the square root of a negative 9, this cannot be done. What number times itself is going to be a negative 9? There aren't any. I can do 3 times 3, but notice that's a positive 3 times a positive 3, which is going to give us a positive answer. I can do a negative 3, but if I multiply it by itself, I have to multiply it by a negative 3 again, which a negative times a negative is a positive. So I cannot get a negative underneath the square root. A square root now. Different indexes, different problems. But underneath a square root, I cannot get a negative because I have to multiply by itself, which means negative times a negative or positive times a positive, which is only going to give me positive answers. So when we have the square root of a negative 9, this is what's known as an imaginary number. I love imaginary numbers, but we're not going to do them this class. You are off the hook for something called imaginary numbers this class. If you take an intermediate algebra, you will have them. If you're here for tech math, you will have them, maybe not in tech math, but eventually you will come to negative numbers as well. I can't remember if they're in tech math. Oh, we'll get it figured out. All right? But what do we do with the irrational numbers? The numbers that are not perfect square roots. Well, one of the things we want you to be able to do is to approximate those roots. We want you to figure out where is the square root of 8. This is an irrational number. That means it does not end or repeat. It will keep going. The decimal places will not terminate or end. They will go on for infinitely long trails of decimals, okay? So, do I know what the square root of 8 is? Well, I do. And not because I've done it a million times, but because I can give it an approximation. I know, looking at my square root table, right, this one right here, that 8, 1, 4, 9, the 8 falls between 4 and 9. So that means that the square root of 8 should fall between the square root of 9 and the square root of 4. Since I know my perfect squares, I can fit the square root of 8. Since 8 is between 9 and 4, the square root of 8 should fall between the square root of 9 and the square root of 4. This means square root of 4 is 2, which is less than the square root of 8, which is less than 3. So the square root of 8 falls somewhere between 2 and 3. And since 8 is way closer to 9 than it is to 4, I am going to approximate that the square root of 8 is actually closer to 3. So if I had to throw a decimal on there, I might say like 2.7, maybe? So my guess or approximation is about 2.7. I don't know if I'm right, but I'm going to guess that that's about where it is. So now I'm going to hit the square root button, and I'm going to put an 8 there. Oh, 2.8. Okay. So I was close. It's just a guess. Maybe you would have guessed 2.9. You would have been a little bit closer than me if you'd guessed 2.9. All right? Let's try 90. Where is 90 in terms of perfect squares? If I only look at the radicand, if I only look at the 90, and then I come over here to my list of perfect squares, and I look at the numbers in red, I see that 90 would fall between the 100 and the 81. So 90, the radicand here, would be less than the 100. So it has to be less than the square root of 100. And it has to be more than the square root of 81. So that 90 is going to fall between 9 and 10. So the square root of 90 as a decimal has to fall someplace between 9 and 10. Not knowing exactly where it is, I'm going to make a guess. And I'm going to guess 90 is a little bit closer to 100, but I've got to be at least 9. So I'm going to say it's about 9 point. This time I'm going to go 9.8 because the last time I should have used an 8 and I didn't. Okay, so now I'm going to try square root 90 equals, well, look at that, I was high, 9.420. Okay, but I mean, I'm within 1. 10, 9, 9.5 versus 9.8. We're pretty good. We're pretty good. All right. But hopefully with that, you can see it is possible to get close, but this calculator, the ability to use the square root key on a calculator is going to be key here. The square root of 15, I'm just going to take the square root 15, and I'm going to approximate this according to this to the nearest hundredth. The hundredth, that would be the ones, the tenths, the hundredths. So I'm going to look at that 2, and that's going to keep the 7 the same. So this is going to be approximately 3.87. And that's what I'm going to get when I round the square root of 15 to the nearest hundredth. Similarly, I have 9 times the square root of 22 over 5. Now to do 9 times the square root of 22, I'm going to hit my 9 first times second square root 22. I'm going to close my parentheses. If you don't close the parentheses, this will give you the wrong answer. Then I'm going to divide by 5. And that gives me about hundredths place is ones, tenths, hundredths. And again, that 2 is going to keep the 4 the same. So this is going to be 8.44. Okay, I'm not going to spend too much time on this. It is really just putting it into your calculator and seeing how it goes from there, right? We also have a part of this is, can you classify these roots as rational, irrational, or imaginary? And as a reminder, the rational turn out to be ending or terminating numbers. So if I do the second 256 and I get that that is 16, so this is a rational square root. If I have the square root of a negative 16, I cannot have a negative underneath the square root. This one is imaginary because I have the negative under the square root. Negative is what gives it away to being imaginary. And that makes me think number 13 might be irrational. So I'm going to do second. Oh, you know what I should show you? Just for a second, just so you see. So if I do, whoops, I turned it off. If I do second square root and then I do negative 16, watch what happens on my calculator. So I will get a domain error on my calculator. Domain errors generally mean that you cannot complete that problem, that the function or the square root does not exist there. And that's true. We know it doesn't exist for negative numbers. So if you get a domain error, that is likely the imaginary number in this situation. All right. Okay. The last one here is the square root of 45. So I'm going to clear this. Second square root, oh, nope, clear. There we go. Second square root 45. And you see how the decimal places fill out my calculator? And if you do this on a phone or on a computer, you'll get very many more. There is nothing repeating. 393, nope. So what we're going to do is we are just going to keep, well, we're not going to keep anything because we don't need to know what this is. Because the decimals keep going, we would say this is irrational. This would be about 6.708203932, and it just keeps going. We don't know what they are, but it's going to just keep going. When it does keep going like that, that is irrational. All right. What else do we have in this section? Well, our third goal for today is to graph that square root function. We want you to be able to see what that looks like on a graph. And for that, we're just going to do some function notation and plug it in. So Let's start at the beginning. Our function, or f of x, is the square root of x. So whatever our x values are, we are going to plug that into the square root. So we're going to first do the square root of a -1. And we've talked about this, but you cannot do the square root of a -1. So this does not exist. DNE says it does not exist. I cannot do that. So now I'm going to put 0 in for the x. That's going to be the square root of 0, which is 0. So I have a second point here at 0, 0. First point did not exist. Second point is 0, 0. Third point, I'm going to write it out a little bit better. F of 1 would be the square root of 1. That's 1. Then I would have, let's do, wait. I want them to work. If I do a 2, I'm going to have the square root of 2. And that's not going to work, right? Because if I do a 2, then f of 2 would be the square root of 2, which is going to be about, because that's not a perfect square. So that's not a perfect square. So if I do the square root of 2, I get 1.414. I can't graph that. I don't know where 1.414. I don't. So, So my y value would just be the square root of 2, which is not even an exact number. I can't plot this, right? I mean, I can plot 0, 0, bam. I can plot 1, 1, bam. I can plot 2 square root of 2. I mean, I can't really plot that because it's 1.414. I could guesstimate it, right? But I can't plot it exactly. So I'm going to put it like rightish there. But then I'm going to do myself a favor, and I'm not going to do 3 because 3 doesn't work. I can't do square root of 3. I'm going to skip to 4 because then f of 4 is going to be 2, which is really easy. 1, 2, 3, 4, 2. At least I know where that is and I can plot it, right? That's going to be the 0.42. 5 isn't a perfect square root. 6 isn't a perfect square root. 7, 8, but 9 is. So I could jump to 9 because f of 9 is going to be the square root of 9, which is 3. So then I've got a point at 9, 3. 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. There we go. And there's my third point. And now when I go into graph this line, I can start at 0, 0. I can hit that 1, 1. I can hit that 4, 2. I can hit that 9, 3. And just graph it that way. Then hopefully everything else. It's a nice approximate square root function. But notice that it doesn't exist over here in the negatives because we cannot take the square root of a negative number. So it's not going to exist over here. That's a domain error. When it can't exist over there, that's a domain error. All right, let's try a couple more. So we want to graph f of x is equal to a -2 plus x. So f of 0 would be a -2 plus the square root of 0. I can take the square root of 0, that's 0. So 0 plus a -2 is just a -2. Then we'll do f of 1, which would be -2, whoops, thinking ahead, plus the square root of 1. The square root of 1 is 1 plus a -2. That's going to be a -1. Now, I tried the 2 before and I didn't get anywhere, so I'm going to jump to 4. Then I'm going to do a 9. Should I do a 16? I don't think I have enough room for a 16. So we're just going to do 4 and 9. Oh, I bet I do. Let's try it. All right, so that was 1, -1. All right, what happened with 4? F of 4 would be a -2 plus the square root of 4. Negative 2 plus 2, that's going to give me a 0. What about f of 9? It'd be negative 2 plus the square root of 9. Must be a negative 2 plus 3. This would be a 1. So then I've got the 0.91. And f of 16 is going to be a negative 2 plus the square root of 16. That's going to be 2. All right. Let's see how many of these I can plot, because this graph may not be very conducive. So I've got a 0, negative 2. Bam. I've got a 1, negative 1. Yep. I've got a 4, 0. Okay. I've got a 9, 1. Okay. I can't do 16, 2. But it would be way over here. But we can at least see. Okay, that's interesting. Look at where this was the original one. And when we started with a negative 2, everything just sort of dropped down to. Okay, that makes sense. All right, let's try 15. F of x is 3 times the square root of x. All right. So if we did f of 0, that would be 3 times the square root of 0. That's still 0. If we did f of 1, that's going to be 3 times the square root of 1. Square root of 1 is 1. Times 3 is 3. Now I'm going to do 4 and 9 and 16. I wonder if I'm going to be able to get 16 this time. We'll try. So f of 4 would be 3 times the square root of 4. This would be 3 times 2, which is 6. So 4, 6. If we do f of 9, this would be 3 times the square root of 9, which would be 3 times 3 or 9. So 9, 9. That's a nice point. And if we did 16, f of 16 would be 3 times the square root of 16. That's going to be 3 times 4, which is 12. All right, so now I'm going to use this graph to plot those points. I've got a 0, 0. I've got a 1, 3. I've got a 4, 2, 3, 4, 2, 4, 6. And then I've got a 9, 9. Yeah, that's kind of going to go off screen. All right, so the best I can do is sort of like head it off in that direction. I'm never going to fit 16, 12, but you can see it's going to kind of level off a little bit. But yeah, again, no negatives. No negatives. No negatives. Right? But this is really just graphing at its most basic, plugging in the numbers and chugging out your y values. So, but notice that all 3 of these graphs sort of have the same kind of idea to them. They all start and sort of zoom off. Whoop, whoop. Square root functions do that. They all kind of look similar that way. Right? Okay. So that just brings us to the 4th goal of this section, and that has to do with Pythagoras' theorem. Pythagorean theorem, which we have worked with a little bit already. So just to review, Pythagoras' theorem has to do with right triangles. So you must have a right triangle. In Pythagorean theorem, there are 2 legs, both the A and the B, or the 2 angles or 2 sides that make up the right angle are known as the legs. The 3rd side, or the side opposite, is known as the hypotenuse. So A and B are known as the legs of the right triangle. C, again, is known as the hypotenuse. Some things to keep in mind for right triangles: that A plus B together must be bigger then the value of C, so A and B when added together must be bigger than C, but C has to be bigger than A, and the C value has to be bigger than B. So C is the longest individual side. The length of C must be greater than either two individual sides, but the sum of A and B together, or the sum of the legs, must still be bigger than C, or the value of the hypotenuse. This is important because I find that many students shortcut Pythagoras' theorem by simply saying C is the sum of A and B. It is not. Pythagoras' theorem says that the square of A added to the square of B is equal to the square of C. So Pythagoras' theorem says A squared plus B squared is equal to C squared, right? We're going to be using Pythagoras' theorem and the square root property of equality. I didn't write that out for you, did I? The square root property of equality basically says if A is the same as B, then A squared is equal to B squared. But it's different A's and B's. So if two expressions have the same values, then when you square them, they still are the same, right? We're going to be concentrating on Pythagoras. And when we use square root property of equality in a minute here, I'll sort of show you where that comes in. All right, so we have three problems to do. We have a baseball bat leaning against a dugout. The base of the bat is 28 inches above the ground, and the head of the bat is 15 inches from the wall of the dugout. How long is the bat? All right, so what am I going to do here? I'm going to have the dugout, which, right, chain link fence. Got it. So we're going to have a baseball bat. Do I have a brown one? Maybe I do, maybe I don't. I don't seem to have a brown marker. Oh, maybe we can use this. We'll make it purple. All right, so here's my baseball bat. And it is leaning against the dugout. Opening day was this week, by the way. I know many people are excited about that. So this is a bad baseball bat, although I tried to get the general shape. Okay, so this baseball bat is 28 inches above the ground. So 28 inches above the ground. And the base head of the bat is 15 inches from the wall of the dugout. So 15 here. Okay. How long is the bat? So essentially, in trying to sketch this out, I hope that you see there is a right triangle here with two sides of 28 and 15, and that the right angle would occur between the dugout and the ground, between the dugout and the ground. So using Pythagorean theorem, we would do A squared plus B squared is equal to C squared, where A and B are the legs of the right angle, and C is the hypotenuse, which would represent the length of the bat. So we would have 28 squared plus 15 squared is equal to C squared. I'm going to go ahead and use my calculator. Now you can do this individually. I like to do it in one fell swoop. 28 squared plus 15 squared is going to be 1,009. So now I can use the square root property of equality, which says if C squared is 109, then I can take the square root of both sides. Because if two numbers are squares, then the numbers themselves have to be the same. So now I'm going to do second square root 1,009. Oh, I don't get 31.76. Is about C. Now, note that this could be positive or negative, right? It's C squared, And since I'm going backwards and solving for C, a positive number would work as would a negative, but the negative number doesn't make any sense here because we wouldn't do the length of a baseball bat as a negative number. So how long is this bat? It's about 31.76 inches. Okay. Couple of other things. Note that if I add 28 plus 15 together, I get a number that is greater than my answer, but this answer is bigger than each side individually. 31.76 is bigger than 28, and it is bigger than 15. Okay? It is not bigger than the sum, but it is bigger than each individual. Okay, problem number 17. An architect has designed a 6-foot wide balcony that floats from the wall using an 8-foot wall brace. If one end of the brace is placed at the far point of the balcony, how far down the wall will the other end of the brace be anchored? Okay, so here's my wall. Here's the balcony that floats out. And it is 6 feet wide. We're going to use an 8-foot wall brace. Now, it's important. This may be something that you do not recognize. The 8-foot wall brace is said to come from the edge of the balcony to the wall. So it's got to go something like this. And that's my 8-foot brace. This allows the balcony to float or to look like it's floating off of the edge of the wall. But what they want to know is how far down the wall the brace will be anchored. So I've got this all the way out at the end. That's one anchor. Far point of the balcony anchor right there. How far down the wall? So we want to know this distance. How far down the wall will that be braced? So can you find your right angle? This is still a right triangle. This is 6 feet. This is 8 feet. And this one is missing. Using Pythagoras' theorem, we know that a squared plus b squared has to equal c squared. A and B are the two legs, A, B. C is the hypotenuse. Note that that's different. So now we have x squared plus 6 squared is equal to 8 squared. I cannot do this the same way in my calculator because I cannot add an x squared to a 6 squared. This would be x squared plus 36 is equal to 64. I'm going to subtract the 36 from both sides. X squared is, I want to say that's 28. Let's try 64 minus 36. Yep, is 28. Now, I want to use the square root property of equality. And since x squared is equal to 28, the square root of the x squared is equal to the square root of 28. So second square root 28. Close my parentheses. And I get that x is about 5.29. So we're going to put it down about 5.29 feet. Do we know what that is in feet and inches? Oh, Lord, what if they ask feet and inches? Well, if they ask feet and inches, I'm going to subtract the 5 because I know the whole feet. That'd be 5 whole feet. And then I have to convert that to inches. We did this. We did this last section, I believe. So I'm going to have to take, there are 12 inches in a foot. So I'm going to have to multiply this by the 12 inches in a foot. And I get 5 feet and about 3.5 inches. Yeah. There we go. Woo! Sorry. That's the dog. He scared me. You scared me. right, let's try the last one. He's been good the whole video. Ray purchased a new 60-inch television. The width of the television is 34 inches. Determine the height of the TV. We want you to pay attention to the fact that TV sizes are listed by the length of the diagonal. So when they say they've purchased a new 60-inch television, we're talking about the 60 inches being across this way. So that's where your 60 inches are. The width of the television is 34. Determine the height. So this I do not know. This would be 34 inches. Okay, do you see the right triangle? We've got an A, a B, and C for Pythagoras, which is A squared plus B squared equals C squared. So we've got an x squared plus 34 squared equals 60 squared. I have to do this one not like I did 16 where I didn't know the hypotenuse, but I do know the hypotenuse. So this is going to involve a little subtraction. X squared plus 34 squared is 1156. 60 squared is 3,600. Subtracting the 1156 from both sides, we get 2,444. Now, since that x is squared, as is the 2,444, I can take the square root of each side using the square root property of equality. The square root of x squared is indeed x, and the square root of 2,444, not enough there, not too many, yep, is about 49.44. So that means that the height of the television, the length of the television, the height of the television, is 49.44 inches. Okay. All right, so hopefully that gives you a decent enough intro to the idea of square roots, gets you a little bit back into the swing of things when it comes to square root. And the reminder of Pythagoras' theorem is going to come in handy as we're going to be doing that again in this unit, in this chapter. All right, so let me see if I can get Ozzy. Ozzy is his name. He's quite the beauty. Ozzy, you just barked and went back to sleep? Come here, Bubby. Come here, say hi. Come say hi. Oh, stretching? Were you napping? Were you napping, Oz? Come here. Come say hi, Ozzy. Come on, up. Come on, Bubba. Come on. No. Where are you? Come say hi in the video. Oh. Can you say hi over here? Say hi. There he is. Like, want to get hugs, kisses? Okay. Yeah. Okay. This is my brother's dog. He's staying with me for a little bit. Aren't you? Yeah. Just a little bit. Okay. All right. You go back. You want to go? Oh. Okay. All right. We'll see you next time because I have a feeling Ozzy will still be here. All right. Have a good one.